Hello, everyone. I'm excited to be part of the third international conference on artificial intelligence and logistics engineering, ECAL 2023, holding here in China today, March 11th, up to tomorrow, 12th, 2023. My name is John Efiong of the Department of Computer Science and Engineering at the University, or rather, Obafemi Awolowo University, Nigeria. I will be presenting a research on modeling smart grid instability against cyber attacks in SCADA system networks. This research was conducted by myself, John Efiong, alongside other researchers such as Dr. Bodunde Akiyemi, Professor Emmanuel Olajubu, Professor Ganiyu Aderemo, Professor Isa Ibrahim, and Professor Jules Degila. And this will be the outline I would like to follow. I will do an introduction to the research and then show us some reviews that we've done, the methods that we adopted, the data sets used. Then we'll present results and discussion before drawing conclusion. So starting with introduction, the cyber physical power system, CPPS, which is also called the smart grid, is an heterogeneous, multifaceted system which is expected to provide stability to the power grid. It is expected to be robust and efficient and also reliable. The smart grid is also expected to support resource management and load balancing in the energy value chain. Smart grid stability itself entails maintaining a balance between the energy generated and energy consumed. So what the smart grid stability seeks to establish is that whatever is coming from the power plant goes or rather runs at equilibrium with what goes through the transmission phase, the distribution phase up to the consumption phase. So in the smart grid, there are a number of components like the IED, the SCADA system itself, the HMI, the PLC, the PMU, and the rest of them. The PMU, which is the physical measurement unit, is a popular tool for monitoring voltage stability and for analyzing oscillation stability. So the PMU also helps in estimating power states, monitoring and control of wide area network, both times reactive optimization. It also helps in blackout analysis, real-time electricity costing, and fault detection in the transmission line. So the PMU becomes a vital tool, a vital component of the smart grid because of the functionalities that it performs. So when an attacker directs its attack towards the PMU, and if it is successful, what it does is to put off the PMU from performing its primary functions, and that can inevitably lead to power instability in the electric grid. Furthermore, cyber attack may interfere with the control process of circuit breakers, which may eventually force circuit breakers to respond to external commands, commands that are coming from attackers. So if its circuit breaker is kind of compromised, it can begin to respond to those commands. This can be through command injection or command or data injection, or also time synchronization attack, which we are going to look at in this presentation. So power stability is equivalent to availability of power resources. So if an attacker is able to cause instability in the grid, eventually to be denying the grid of its services to its clients. So it becomes important, therefore, to model smart grid instabilities against attacks. Okay, so by modeling smart grid stability against attacks, it helps to examine the risks associated with cyber attacks and their propensity to affect not only power stability, but the safety of personnel and security of the components of the SCADA network. So in essence, when smart grid instability is modeled against cyber attacks, it provides four major benefits to power system engineers. One, power engineers will be able to respond to attacks based on the ability to point out the problems of specific components. Again, it will help in mitigation strategies, which, when developed, will help in preventing future occurrences of attacks. Third, it will help in regular evaluation of security posture of the organization. And finally, it will help, hopefully help system engineers to engage in a more formidable design and development of resilient physical systems for the power sector. Looking at the necessity for this research, the existing body of knowledge rather focused on mechanical prediction of instability using a plethora of techniques. There is an acute shortage of works and that associate instability with the possibility of cyber attacks. So in this study, we have understudied soft operations of attacks and their propensity to distort the stability of the grid. So basically what we are saying in this research is that not all instability or not all kinds of outages or blackouts are mechanical. They could be due to cyber attacks on the major components of the smart grid. So typically in this paper, we have modeled term synchronization attacks, TSA, and if we also implemented machine learning algorithms for attack identification as a precursor for instability in the smart grid network. So the primary objective of the study is to associate power instability with cyber attacks and provide machine learning-based models for intrusion detection in the smart grid network. So looking at the reviews we've done, efforts have been made in literature to model attacks on smart grid network. For instance, studies by Azamasov, Baum, and Joachim 2018 modeled grid stability with the Central Smart Grid Control, DSGC, based on frequency by measuring the cycles per second of the alternate currents. This, however, was applicable at the power generation phase of the grid process. So the other components, the other phases of the grid were not taken care of. The same authors adopted a decision tree algorithm and space filling designs to implement the DSGC model. In 2018, still Zhang et al. Investigated how the facial measurement units could be used to model a time-synchronized attack in the smart grid network with the aim of revealing tampered data, possible effects on voltage stability, automatic generation control, and others. So this works have been done that more we're going to talk about. Instability was modeled using the delayed dependent stability analysis technique by Mary Rangarajan 2016 and Ye et al. 2017 for a gene value computation of the grid network. So that's it. So in 2011, Kondo et al. Adopted a directed graph method with a dynamic system equation for modeling smart grid attack. 2014, Leo et al. Experimented with a sort of distributed denial of service, the strategy to cause transient instability in the grid using variable structure model or system model. And then in 2020, more recent research was conducted by Wu et al., where they performed an optimal partial feedback attack modeling for command injection attacks and data injection attacks in the grid. Some of the works that model instability against threats and attacks in the physical systems of the power sector have indeed indicated that a multi-agent based technique may be appropriate in detecting and spotting threats in high affinity for causing, with high affinity for causing instability in the smart grid. So a number of works have been done in that direction. For instance, Raman et al. 2017 adopted a multi-agent method. And then similarly, Farage, Hamad, and Condor 2018 proposed a control framework based on multi-agent perspective. Also, Skiva, Dovla, and Friedman 2017 proposed a distributed averaging method of base integral controller to solve the grid. These were dependent on, the multi-agent method for detecting, or rather, yes, detecting threats in the smart grid, or what could cause power instability in the smart grid. To leverage the control of distributed energy resources and reduce transient instability in the grid, as Rekanta and Condor 2016 proposed a differential game theoretic technique or method designed to model the attacker's behavior in the smart grid. There are also a number of techniques that have been used in literature, like the ones listed here, which we've taken time to go through them. These were actually the traditional methods for predicting instability in the grid. So machine learning-based method was eventually adopted to improve on the traditional methods. For instance, in 2021, Briviglieri et al. Proposed an optimized deep learning model for predicting smart grid instability. Also, Wood 2020 proposed an optimized data machine learning network-based model for predicting stability for the centralized power grid. So eventually, artificial intelligence was brought in with machine learning and deep learning methods eventually adopted for predicting causes of instability associated with attacks in the grid. So a recent study this was done in 2022 by Dewangan et al. Leveraged the genetic algorithm to predict instability in the grid using 4-feature-based data set extracted from UCIML repository, which was able to yield an accuracy of 98%. This data set actually did not depict the DSGC system, which we are using in this work. And the proposed model was not associated with cyber attack mechanisms in the grid. So our study employs machine learning techniques to model instability and associate same with cyber attacks and provide insights that can help develop intrusion detection systems and possible prevention in the smart grid network. So looking at the methods, first here we present the attack instability modeling. The attack stability modeling can follow a dynamic system-based technique where the physical component of the physical system will follow differential equations utilizing energy flow, while a cyber component will follow differential equations using information flow. Of course, it is expected that the cyber components of the CPS will disturb the physical components. As such, the stimulant of the state of the generator, typically frequency and angle in the rotor swing equation of the generator, could be used to model perturbations. So this study adopted the technique used by Srikanth and Kothar 2016. Also, we were able to model time synchronization attack, TSA. The TSA is an attack that exploits the wide area monitoring systems, WAMS, and targets vulnerable networks with dynamic data exchanges at the nodes. The technique is to modify the time synchronization at the endpoint and thereby causing cascading failures. So in the electric grid, the TSA attacker can build a vector to control the synchronization generator to remotely control the distributed energy resources remotely. This will eventually enable the attacker to have lateral access to the system and enforce the instability of the smart grid. So when we modeled the TSA international land fault detection, equation 1 was more appropriate for that modeling. And then I think this setting, sorry for this setting, it's an error. Here it's supposed to be model TSA on voltage stability monitoring. And this was done using equations 2, 3, and 4. And then modeling TSA on event location, this was done using equation 5. So looking at the data sets, first of all, we need to look at this intra smart grid control model, the DSGC model. So the DSGC model is a system that monitors frequency, and ensures a strict observance of the state of equilibrium between the power generated and consumed. So like we said, so DSGC allows power stability to be modeled where there is a desire to ensure that there is an equilibrium between the generated power and the consumed power. So the DSGC model can be expressed mathematically using equation 6, as shown here. The data set used for our experiments was the electrical grid stability simulated data set created by Azamasov, Baum, and 2018 to support the DSGC projects. The dataset was generated using a grid stability reference for node star network simulation, as seen in figure 1, containing 10,000 samples. And the original dataset contained 12 features and 2 target classes. For our experimental setup, the experiment was carried out on Weka, which allows for attribute selection, data pre-processing, classification, clustering, association, linking, visualization, and cross-validation. So eventually we were able to split our data set into 75% for training and 25% for testing and evaluation. We also projected the unstable class into anomaly class and the stable class into normal states of the system. So looking at the results, a total of 10 machine learning algorithms were implemented, and the results are shown in this table 1 and also in table 2, which I will display shortly. The random forest classifier demonstrated the best result in all the benefit metrics, yielding 92%, 91.9, 92, and 91.9% for accuracy, precision, recall, and F measure, respectively. The ensemble classifier closely followed this random forest, where bagging yielded 90.9, 89.9, sorry, 90.0, 89.9, 90.0, and 89 for accuracy. As we can see on this table, the table really shows the high performances of the random forest and also bagging. It also shows all the algorithms that were implemented and the metrics, including the ROC area, the result of the ROC area curve. So looking at the model evaluation metrics as shown in table 2, we can also see that the results are displayed. You can look at the performance of each of these classifiers and the metrics that we use, the true positive rates, the false positive rates, the mean absolute error, and the root mean square error of each of these classifiers that we used. So the last column of this table 1, the last column of table 1 here, the ROSC, shows that random forest has 97%, while bagging has 96%. The PAROT and naive Bayes had an equal result of 92%, while the lab tree and AD tree had 91.0 and 91.9. Respectively for the ROC area under curve. So a random forest of 100 trees was constructed while considering 4 random features, and the out of back error was 0.0084. That is significantly good enough This shows the efficiency of the random forest classifier in modeling instabilities against smart grid attacks. PAR generated 65 rules, and JRIP generated 51 rules. The J48 tree classifiers had a total of 813 trees with 407 leaves. So these were the results obtained as shown on the table. The conversion matrices of the classifier showed that random forest had a true positive rate of 92% as shown on the table, which is the highest, and the false positive rate of 0.11, which is the lowest, and that is a fantastic result coming from random forest. The MAE and ROMS EC of the random forest were 0.18 and 0.025 respectively. This also showed a high performance by the random forest. So bagging a technique produced a true positive rates of 90%, that's high, and the false positive rate of 0.13. The mean absolute error and the root mean square of bagging were 0.17 and 0.27 respectively. Okay, so these results also actually shows which of these classifiers is suitable for building models for detecting attacks on a smart grid through instability. Conclusion. The utility service providing domain is delicate and requires adequate care and attention to all eventualities. This study proposes that not all power failures or instability results from mechanical faults or natural occurrences. Targeted attacks at specific components of the grid, like the PMU that we talked about, can result in serious dangers. So cyber attacks on a smart grid can prompt communication delays and obviously cause service denials and puncture data exchanges between the PMU and the control center, or even take control of the entire control systems or the entire plant. This ultimately results in power instability, which we technically refer to as denial of service or DOS attack. We have modeled term synchronization attack in this research, which is still the attack that establishes an attack vector or increases an attack surface such that the attacker takes control of the synchronization generator versus remotely controlling the DERs. This attack technique can be catastrophic due to the several other components and processes that the DER usually manages. In addition, the TSA has the propensity to open the network for DDoS. So modeling attacks in the smart grid network helps in identifying threats and developing mitigation mechanism. So in this paper, we have demonstrated 10 machine learning algorithms that can help model smart grid instability against cyber attacks on our physical power systems and other critical infrastructure. We've shown that random forest classifier of the trees methods and bagging classifier of the ensemble techniques were found to be more promising and can hence be tuned to provide high accuracy, precision, recall, and measure for intrusion detection in the smart grid. This result have implication for effective threat modeling in smart grid network. The idea portrayed in this research will help in attacks identification, threats classification, prediction, intrusion detection, and developing mitigation techniques or processes. We emphasize that future studies may consider modeling other kinds of attacks in the network by leveraging deep learning algorithms. So these are the references that we refer to in the study. Thank you for listening. Kindly drop your questions and I will attempt to answer them. Thank you for listening.